Hello everyone, welcome back to The Art of Engineering Efficiency Season 2 Episode 4. In last episode, we have seen combination of language model, vision model and image to text description model. In this episode, we are stepping into something bit more ahead of using multimodal AIs and something which is more powerful that makes models from generic to specialized. From knowing nothing about your personal data or enterprise data to fully knowing exactly what we need. That's what we are talking about RAG, Retrieval Augmented Generation. If we look at any AI assisted chatbot kind of applications, they used to remember all our conversation even we restart them after a month. RAG makes it possible that they store all our conversation history and everything into a database that they can fetch at any point of time. And we can also run AI applications with the private and enterprise level datasets. So this episode is exactly what we are going to drive through with the practical demos. So let's get started how to build an AI application aligned with the RAG pipeline with the local knowledge base. So this is the first example where we try to demonstrate the basic RAG pipeline using a completely local knowledge base. This Mistral bot is an extension to the previously demonstrated Mistral bot. This bot is enhanced with the RAG pipeline. So let's quickly run and see how this works, and later we will go in depth of what are the major building blocks of this RAG pipeline. Let me go to terminal. Mistral RAG bot static knowledge. Okay, let me show you while it's running. So this is the project structure of this RAG pipeline. We have this RAG static knowledge where I have kept one PDF document here, Little Red Riding Hood, a small story for kids. And we will use this as a knowledge base. We'll ask few queries to language model and see how it responds. The bot is running. Now I can ask who is the lead character of the story. So it went to fetch, it said Little Red Riding Hood. Okay, before asking queries, let me give a brief of this story. Let me open this PDF so that you will understand. The story is about a small kid, Little Red Riding Hood. His grandma is not feeling well, so his mother sent him with some bottle of fresh milk, bread, and butter to give it to his grandmother. So on the way to his grandmother's home, he will come across a cunning wolf, and the wolf says, "Go pluck some flowers." And meanwhile, the wolf goes to the grandma's house and eats her. She tries to be her grandma, and she wants to eat this little kid also. And finally, some other person who is on the forest help cut the wolf. These both persons sprang out of the wolf. So that's how the story ends. Let's go back to the demonstration. So that's why it said Little Red Riding Hood, the lead character of the story. Where and why the Little Red Riding Hood is headed. It said the Little Red Riding Hood is headed to her grandmother's house. She's carrying a basket of food for her grandmother who is sick. This is 100% accurate from the PDF what is fed to this RAG pipeline. This is a small example. And let me ask one more final question. What happened finally? Because we are running on a low computational power system, we have given a small PDF document, but if we have a good computational power, we can go for a huge document, many paragraphs, many pages, so that this language model will be able to process context and will be able to answer our questions. So finally, the assistant answered as the wolf ate grandma according to the traditional ending story. However, there are alternative endings that have been developed over time. One popular alternative ending is that grandma outsmarts the wolf by leading him into a trap or pot of boiling water, and then she's able to escape and save herself. This is something hallucinated by the model, but we can ask one more question straight away. What is alternate ending of the story? An alternative ending of the story is where the wolf is defeated by the woodsman. The woodsman hears the wolf's laughter and follows the sound to find wolves in grandma's house. He shoots the wolf and saves the grandma. A little later, Riding Hood. In this version, the wolf is punished for its action on grandma. This is how a classic RAG pipeline works. Now let's go to the core building blocks of this classic RAG pipeline. As a first step, we call this bot. We give the static knowledge directory. So whatever documents are there in this directory will be fed as a knowledge base to the language model. That's the idea. I have given this as per my system's document directory and this projects directory. You can change it to once the Mistral bot is initialized with this directory, then as a first step, we initialize the static knowledge and then we load this with the contents of the static directory. So as soon as we start loading it, right, so we have some predefined file formats which are supported to read the text out of the files. Using these files, we'll process them and extract the text from either image, PDF or text source files. And once we have the data, then we add it to a vector database. So this is the key element as part of the RAG pipeline. So till now we have seen whatever the context or whatever the knowledge base we are setting to the language model is all in the live memory. I mean, if once the application is stopped, then there is no way we are going to get back them. So that's how they worked. But now we are bringing a DB here, which is aligned with the language models, that is vector DB. This vector data is actually initialized as soon as the static knowledge is initialized. It holds a reference here. In this vector data store, it has all the key elements which are necessary to hold or transform the text into a vector database. So the key elements of this vector data store are, first thing is FAISS, which is Facebook's AI similarity search supported by Meta, where it can retrieve the data based on a simple keyword search, unlike the traditional databases. Sentence transformer, this is the first thing actually the text goes into, and it will convert it as an embeddings that is understandable by the vector database. So sentence formatter is a crucial part of this RAG pipeline. And then we have few configurational attributes, and this index is a part of FAISS to access the data with the similarity search. That's what this indexing is about. This part I'll explain later. This is for the persistent store. We'll see that in the later demonstrations. This is what happens as soon as we initialize the vector data store. When we actually try to add the documents, I mean list of text content, then first it feeds it to the embedder and encodes it and get the embeddings of it, of the data that we fed to it, and then it will add it to the index. This index is nothing but the FAISS reference. So it will add that embeddings to the vector database reference, and a doc store which acts as a metadata, actual data which we feed it to the vector data store. That's how we convert our documents to text and text to embeddings, and then we feed it to the vector database. So this is the usual process that happens in this RAG pipeline. Now we understood how the data is coming and sitting in the vector database. Now let's see this RAG pipeline of the Mistral bot. What happens when the user actually queries something? As soon as the user queries something, it comes here. The user input is fed to static knowledge class. It will retrieve based on the user input. Let's go to the static knowledge. It internally directly goes through the vector data store. So here that query comes to this vector data store, and here again it goes to this sentence transformer, pass the query, gets the query embedding of that. Okay, now it is also converted as an embedding. This query embedding is passed to the vector database reference, like how we query the SQLite or other traditional databases. Same thing happens here too, but with a similarity search. It doesn't have any specific querying parameters or attributes. So we simply pass the query in the form of query embedding, and we get the indices of it from the vector database. So here we get the distances and the indices. Using the indices, we get the reference of the doc store, I mean literal meaning of that index, which was actually stored in the doc store when we are adding the documents. Using these indices, we take the actual reference of the content which is present in the doc store, and we return as part of the retrieve class. Then the retrieval information reaches the bot system, and from here the usual process starts again. We set the context as a whatever data is retrieved, and then we build the prompt by setting the context and user input. And this is the usual process what we have seen in previous demonstrations as well. So this is how a classic RAG pipeline works locally with the static data reference. So if you are interested, earlier we also developed a Ollama bot as well, which is shared in the previous demonstrations. I do have an example for that too. Go check that out, and how the classic RAG pipeline is easily integrated with Ollama bot as well. I hope the demo is pretty much good and understandable. The reason RAG works so well is the language models do generalize the context or the description or the content what we provide to it. But RAG actually memorizes whatever context we give to it. It's like intelligence that they can memorize on demand. Whenever they want, they can recall it using the RAG pipeline. But what if we need something more than just a static information, where an AI application aligns with the dynamic knowledge base within a RAG pipeline? So let's see how the application works with that concept. So this is basically a RAG pipeline supported by dynamic knowledge, where the knowledge is fed through an API service. In previous demonstration, we have seen the knowledge is fed by referring a local document. But here in this example, we are going to feed the information dynamically from the API source. So let's quickly run this application, this Ollama bot. So previous application was built using Mistral bot. Now this application I built using Ollama bot, which was demonstrated in our earlier episodes. So I just tweaked it a bit. It aligns with the RAG pipeline. So first I will run this. Then we will go through the internal building blocks of this RAG pipeline. Python, Ollama, RAGbot, dynamic knowledge. So the bot started running now. I have fed few news APIs here so that whatever user inputs here, we are going to fetch it. I'll ask simply put a query like what is happening between US and China. So I'm fetching information from 3 news resources which are open sourced. So let's see what it answers actually. So it said President Donald Trump issued an executive introducing new tariffs, and let's ask one more, what is happening in Nepal. So these resources, sometimes they may be outdated a bit, but I think there is no news about Nepal from the news sources that are available to me. Let me ask any latest news about celebrities. Seems like we got a news here. There is some news about celebrities from the news sources which I am relying on. This is how dynamic RAG pipeline works. Let me exit this. Well, let's go to the core building blocks of this dynamic RAG pipeline. The pipeline is more or less similar to what we have seen for the static knowledge base. Only few things will get changed here. Instead of reading the data from document, we're reading it from a API. So dynamic knowledge having a news classes which I created by myself to pull the news from various sources, news API, media stack, and news status. At least one of the hosts might be having what I'm asking for. So that's why I have chosen 3 different sources. And once I get the data from these sources, then I prepare the news as a text format in the same way that we did for the documents. And once we have knowledge base, which news is ready, then again it's the same step that we feed the vector data with the news content, and again we retrieve based on the query. Major difference between the previous and current one is in static knowledge we updated the data even before queried. That means we know the context that we are going to ask queries. That means it's a purely private and local. We dumped the entire document to the vector database in the first place. Then we started accepting the queries from the user. Unlike the static one, this is dynamic. We need to look for the real-time data. Here, as soon as the user asks the query, we hit the API and we get the latest information and feed it to the vector database, and then we retrieve the data which is relevant to the user query from the vector database. That's how the dynamic knowledge RAG pipeline works in the first place. I hope the demo is pretty much good. So this demonstration actually represents how we can club up-to-date information with the static and restricted information within the organization so that the AI application stays updated all the time with the latest information. With this concept, we can actually build many kind of applications like chat gpt that stays up to date, enterprise dashboards, monitoring bots, research co-pilots. We can build similar kind of applications, but out of all this, one thing that is really missing, if we look at in the past two demonstrations, every time the AI application is dependent on the data to fetch every time when it launches. When we relaunch the application, the same steps need to be repeated to capture the knowledge base with the language model. To address that gap, now we are going to see how we can make use of the persistent storage within a RAG pipeline AI application. So unlike the previous demonstrations, whether it is a static knowledge base or a dynamic knowledge base is actually available only when the application is running. So we haven't seen how we can maintain the persistent storage of the vector database. So let's see how we can do it. So I am taking Mistral board as an example, which we have seen in the static knowledge demonstration. The key part of this caching lies in the vector data store, which we discussed in previously, where we have the key building blocks of vector database like FAISS, sentence transformer. I mentioned previously, we'll be discussing in the later phase of the demonstration. So this index path is actually a vector database path, and this mapping path is metadata's file path. As I left a comment here, we simply uncomment this to load the documents, and at the time of adding the documents, we simply uncomment this to save the documents. So what this will do is, as soon as when we try to load the documents, then internally it triggers this add documents. Previously, we are maintaining metadata in the live memory. Once after updating the live memory, we are handing it over to save the documents to database file, which is located physically in our system. So let's see what does this save document actually does in first place. This save document takes the FAS reference and it writes the available index of the current index. Self.index holds the latest information up to date, as in when the data comes to this vector data store, it's get added to the index in the form of embeddings. So this will be available in index, and we give this reference and the index path, both will be given here to the FAISS to write it. This index path is a database file path. The FAISS takes care of it to store the entire vector database into this file path, and I am using Pickle to save the metadata. Instead of this, we can also go for the traditional databases. So this is just an option. For me, it is easy to use at this point of demonstration and experimentation. So that's why I went for Pickle. It dumps the metadata into whatever is given in this mapping path. Now, after doing this, whatever documents we have given along with that metadata and vector database references are permanently stored in our systems. So that's how we cache the information in our local system. Now, let's see how we actually load the information. So load documents is similar to any other kind of file operations. Previously, we wrote the information to given index path or a mapping path. Now we are going to read the information from the given index path and mapping path and hold their references. Post that, when we start retrieving, the queries will go how they worked previously. There won't be any difference to that because we cache the indices and the doc store references. The same will be retained from the cached databases, or queries will be executed. I would like to add a bit comment here. So because I made it as a generic one to demonstrate both persistent and non-persistent, so we need to tweak this a bit. I will be doing that change now. I have given a clear instruction here where we actually call this knowledge load. At the time of experimentation from your side, you can make this change and make it run. To demonstrate how we persist the storage, I will load the documents. I haven't cached anything, so I will leave it uncommented. First time, I will uncomment the saved documents. First, it will save the documents. Next time I run the application, I will comment this, because if I don't comment, then the documents will be fed back to the vector data store from the RAG pipeline. There is no logic here in place to identify whether document is already cached or not. Ideally, we can have as an enhancement to this. So let's run the application now. I'm running the same Red Riding Robin Hood story now. So this is where the static knowledge, the little red riding hood is actually, and this is the vector data store. Right now there is no information cached at this point. Let's see the same physical path once we run the application. Let me clear this. Python, yeah, same script I'm running. Application is running now. Now let's go and check the physical directory of our vector data store or the static knowledge. So here in our project directory, we are seeing two freshly created files from the knowledge base what we fed from the static knowledge. The data is cached, so I won't be running any query now. I will just exit. Then I will, so now let's comment this line where we actually give the document directory and save it. Let's run this application and see how the persistent storage actually works. Earlier, we haven't asked any question because that time we are loading the document into the persistent storage. Let's ask who is the end character in the Red Riding Hood story. Seems it identified the semantic search from the vector database. Okay, the lead character in the Red Riding Hood story is Little Red Riding Hood. Okay, yeah, that is correct. Let's ask who is Red Riding Hood is helping and why. So here the fairy tale Little Red Riding Hood helping her grandmother who is sick. She carries a basket of food and other items to her grandmother's house, which is in the woods. Here's something this model hallucinated. It shared like 90% of the answer is actually from the given context. Basically, model is able to point to the persistent storage which is saved in the previous run. So now the context or the knowledge base is fed from the persistent storage, and that's how a persistent storage works in the RAG pipeline. I hope this demo is very much interesting and pretty much understandable. This is the basic kind of architecture that has been used in many popular chat-based applications or AI assistant systems. With this, what we can say is we are no longer using any language models. We are actually augmenting them. The key takeaway from the today's episode is we have learned how to feed language model knowledge base from the local document sources like PDFs, images, and whatever text content sources we have, and we have learned how to feed the online knowledge base to the language model, and finally we learned how to build a persistent vector database and how to make language model answer more accurate to the realistic information. Next episode, we are going to jump into even bigger concept. We'll explore language models that take actions, multi-step reasoning tools, planning and workflows, how to build a full-fledged local agent, no limits, no cloud, no rate limits, no token limits. It's going to be the most exciting episode yet. Until then, keep building, keep experimenting, always try to stay ahead of the curve. Stay tuned and thank you for watching.